So it looks like you're gonna get a during the exam. Are we on yet? Not yet.
We are in now.
Okay. Hi.
Hey.
Actually, Zuko is his last name. Gilberto, I think. Enrique?
I'm not sure.
I think it's Zuko. What happened? All the incoming students, their first and last names were switched over. So how do you keep it fixed?
It is fixed now.
Oh, you managed to be able to
I don't
fix
even know
it.
why I put this in.
Right, right. But oh, I see. That was
So it's
okay.
just the fixed camera.
Right. No, yeah, because yesterday you had to put that thing there, right, to keep it in the spot.
I did at the last second, and I
But
should have
there's
just
another
turned
way.
it off. I should have just turned
Oh,
it
if you
off.
just take off the power, that's it. Just turn it off. It doesn't turn anymore.
Well, it has an internal battery.
All right.
Anyway.
Okay. Oh, no chalk. That's what I
There's
need.
one piece there.
Yeah, one
I've been noticing.
piece there. I'm gonna need more than that because as soon as I break that, I'm gonna go next door. Tell them, hold the fort, hold the fort. Oh, the caution is going out, not in. Okay. Joanne, did you put that sign on that if you enter this room, you will be filmed? That's not your sign, right?
No.
No. Okay. Are we on?
Yes.
Good afternoon. So the agenda. Problem 2. Do I have any issues? Oh yeah, I want to just comment on the textbook, page 369. This has nothing to do with the test. Don't look at any significance. This is just a comment that was made, an interesting relationship that Enrique, is Enrique Zucco there? He's in Brazil. You know him?
Yeah.
So he's not going to be on.
He's coming.
Oh, he'll be on remotely.
Yeah.
Oh, interesting. Should we wait for him? Oh, you were chatting with him.
Yeah.
Interesting. Yeah, so I just want to make a comment because he sent me to page 369, so I had a look at it, and interesting. So I just wanted to comment on that. I have I looked at Piazza. I didn't find anything earth-shattering, but there were a few things. First of all, I wanted to let you know that the learning objectives, learning outcomes, are all up except for day 5. I'm still drafting day 5, but all the other ones are up. So you may want to have a look at them. It's kind of a skill. I don't know. I hope you understand me. I hope you recognize what you read and say, oh, if there's any comment you want to make about the learning outcomes that they don't ring right, or you don't think you'll learn how to do that, or anything like that, let me know, because I'm kind of new at making up learning outcomes. This is a new pedagogical tool, at least for me. Yeah, there was an issue with export to Excel. Are you still having problems if you run the simulation model that it takes a long time to export to Excel? I had that experience initially, but not later. Are you using? It seems to be working on all. It works a little bit differently depending on your browser. I always used it on Chrome. As far as on the final exam, you'll be running it on Firefox, because Chrome crashes ECF, and IE Explorer, Explorer is fine, but you can run on Firefox. That's what we recommend that you run it on Firefox. We made it big so that you don't have to scroll through that little menu. Yeah, we had no problem with export to Excel. Somebody had asked the initial samples, how many initial samples should you pick? And 25 is kind of the number that is bandied around as having a starting point. I was told, it might change, but I was told that when we expect you to create a data set with a simulation, with a gears model, it might take 2-3 minutes or 3-4 minutes for it to run, even at max speed. So you just set it to run and work on other stuff, okay? And then when it pops up, you can export it. So don't be alarmed by the fact, because if she asks you to take a decent number of sample size and a decent number of initial samples, then it's going to take a little while. And that's simulation models. Yeah, I have no other thing. Is there any other questions, areas that you don't understand? Yes? No? Everybody is okay? There's no... Anybody from the crowd, the chat? Just waiting to hear words of wisdom. I don't know. Okay, and I'm still after that Weibull option inside the T-chart, but you don't need to worry about it. Okay, so if Enrique is here, I will talk about item 2, but if not, I'll go straight to problem 2. So you let me know when he comes. Is that okay? Since you know, you can see the list there. Oh, it doesn't say who's there. Oh, I see. Enrique, are you there? Is Enrique's first name? You call him Zuko? Yeah, Zuko. Oh, Zuko is his name. Okay, Zuko, are you there?
Oh, there is something.
What did he say? Standardizing means this. So we're talking about standardizing. When you say the word standardizing is to take Z, to take X minus mu over sigma. And sometimes you need, depends what sigma is. Sometimes sigma could be over root n. But that is standardizing. You're taking from the original units of the problem to so that if X is distributed with mean mu and variance sigma squared, then Z will be distributed with n 0, 1. That's what standardization means. So there are some options. There are some times when standardization is a good idea. We've talked about this. For example, if the sample size is varying, then you can either have varying upper and lower control bounds, or you can standardize, and then you get rid of that. Then you have a constant upper and lower bound off. For your standardized control chart, if you have changing n, like the first sample has 5, the second sample has 3, the third sample has 12, what would be upper and lower bound on the control chart for Z? Well, you're trying to determine, what determines the controls, upper and lower control bounds? Yeah, that's what they're called, but what determines where you put them? What is that? Where do we normally put them? Plus or minus 3. Plus or minus 3 standard deviations. Right? Plus or minus 3 standard deviations. Okay. Plus or minus 3 standard deviations. So once you've standardized it, then what will be the standard deviation of Z? Thank you. So then the control limits will be plus or minus 3. Okay? So you have a choice between lower and upper bounds that go, or if the boss says, I don't like that, can you get it same? And then you standardize it. So he says, what the heck is that? They said, well, I standardize. Well, now it doesn't tell me anything, because Z, what units is Z in? Right? He says, go back to the other one. And then you end up taking the average, which is the wrong thing to do, of all the n's. But that's often what's done in practice. You know, I'll just tell you an anecdote. I was building a simulation model for Pratt & Whitney, and you know, they give me data. And I run the data through the model, I fit distributions, I do the whole thing, and I get garbage. The simulation model just does unreasonable things. And so I go back to the client and I said, you know, I ran the data. He says, where'd you get the data from? I said, well, I got it from these reports. Oh, those are management reports. Don't pay any attention to those. You want the real stuff. You want the real data. He says, but that's very ugly, they say. Are you sure you want, yeah, just give me the ugly, real stuff. I don't care how pretty it is. I just want the real numbers. And they gave me the real numbers and everything worked fine. So when things go up for a management presentation, things very often get simplified, and because they sort of don't mind a little bit of an error in order to make things simpler, you know, keep it simple kind of thing. And so they might take an average of all the n's. But yes. Yes, hi. How's Brazil? Yes, yeah. The idea with the QSUM is that I take you on a tour on how it gets developed. Okay, just like I described to you, that I do regardless. It's a graduate course, and I show you how it was developed. But the QSUM chart is the last one, right? I mean, I have that error, I have that AI -1 in there all over. That's a CI -1, right? But with that corrected, that's the last one. Yeah. And the K, the capital K, when n is greater than 1, you have to divide by root n. Okay, because you're plotting, you're accumulating differences of x bar. So just to make sure I answer the question was.
For the QSUM, you need to do all these steps?
No, you don't need to do all the steps. I mean, not unless I really would go, that would take a long time. You know, I could make a whole exam saying, describe and show step by step the development of a QSUM, but then I would only get to ask you about the QSUM and not about anything else, and doesn't make that much sense. Okay. So that's the answer. Yeah, so I can talk about these. Zuko is here. I can talk about the other thing. I don't have that much to say, but I have something to say. So I'm just going, yes, go ahead.
May I ask one more?
Sure, please.
Can you talk about how to use the FIR to detect the early shifts?
Yes. Fair enough. FIR. Okay. So let me do this quickly. 3 and 2 and then 1, unless something else comes up. So I'll always do the problem last. Okay. So on page 369 of the text, and this is I'm not quoting, but I'm just saying this is the development that they do. They say that CPM is always less than CP. Somebody showed that CPM is always less than CP. I told you yesterday that CP is the most optimistic. So somebody actually proved that CPM is less than USL, is less than CP, and that's equal to USL minus LSL over 6 sigma. Okay. Now, what happens if it turns out that what happens if sigma happens to be the difference between mu minus t? So what that means is that your target, you're off target. Okay, you're not producing on target. So you're off target, but you're off target by 1 standard deviation. And so that may mean, well, the standard deviation is a result, so you don't have control over that, right? Without changing the process, your numbers are you're gonna estimate the standard deviation of the process, sigma naught, and you're gonna have some number. So this is fixed, and that is fixed. But let's say that you set the target such that the target you want to be 1 standard deviation away from it. Okay. So if that is true, and that's sort of key, if that is true, then you can this here becomes equal to USL minus LSL over 6 mu minus t. You know, just, okay, that's that. Okay, and now suppose that CPM is greater than 1. So you have nice capability there, okay? Then if CPM is greater than 1, so if you have here a chart, and this is 1, okay, and CPM lies higher than that, and that expression is higher than CPM, so CPM is somewhere here. This is 1, and this is CPM, right? It's higher than 1, and that is higher than that. So that means that the USL minus LSL over 6 mu minus t is also greater than 1. Okay, and that means that mu minus t is less than, because the mu minus t goes up there, so the mu minus t is going to be less than USL minus LSL over 6. Okay, so yesterday I made a comment that sigma has to be 1. That was wrong. Okay, what you assume is that if your target is such and that, then you get this interesting relationship that if CPM is greater than 1, then by necessity, the difference between your target and your mean is going to be less than this expression here. Zuko found it interesting, and being practitioner, I don't want to take that lightly, but this is just my comment on how we got to that. Okay, so does that, Zuko, does that elicit any reaction from you? No, that's fine. I just wanted to share that. So this is how it came about. So CPM is always less than CP, but then you need this relationship here. This is what bothers me. I guess very often your target could be off by 1 standard deviation. And if that's the case, if you have a capability, if you're capable, if your CPM is greater than 1, then the difference between your target and your current is going to be less than that amount there. That's as far as I took it. Okay, so I read it, I looked at it, interpreted it. I'm a little bit in terms of the so what, in terms of what you're responsible for. This is not meant for that. It's just meant to comment, given that he thought that this relationship was interesting. I just wanted to show how we got to it. Yeah. Oh, okay. So we did not, let's say our simulation model does not include missing data. If you're working for a real enterprise, right, you may occasionally have a glitch in the computer systems or in the manual systems and the data item is missing, okay? And if the data item is missing, then usually it's an asterisk in Minitab, okay? And there may be an automatic system that is doing that. So you import your data, you get a whole bunch of asterisks. You don't want Minitab to hiccup. So you click that and saying, you know, just count the non-missing ones, right? And it's not something that we made use of. So in the context of this course, we never check it. I never pay any attention to it. The only time I did use that is when I wanted to create a chart which only had 1 point, you know, make it look pretty. I used that, but that was sort of like a minor little diversion. Yeah, it does. Yes, it does. But that's only true if sigma is equal to mu minus t. That's where I'm sort of hiccup and, yeah, okay, if that's true, yeah, then that's true. But that's, okay. It's not true in general. That's what I wanted to make clear. This is not just the general relationship. This depends on that. Okay, so now, yeah, let me, where are we? So I think, yeah, that was my value added to this, that to make it clear that it does depend on that being true. FIR. Okay, so FIR. So you have some kind of bound, and QSUM looks like this. If everything is under control, it's going to go back to 0. It's going to go back to 0. It's going to go back to 0. And then all of a sudden, it detects. I was very impressed. You know, I did these videos while I was doing this. Okay, I didn't do this for you. I did it for okay, because I found it interesting to see what happens. So now you might say, well, you know, we have so much material. Why are you adding this? But I think it's interesting to watch that it actually detects it, and then it goes there and it detects it, and sure it doesn't detect it. Okay, so so now you've detected it, and so you now know, in answer to your question about FIR, right? Now you know, and this is H, right? Right? Not little h. You know, we have so this is H. So now we're there. Now we look at the assignable cause. And we found that the air conditioner had shut off, and that's what caused this whole thing to shut off. That's just an example, okay? Now we start the thing again. And we started, okay, we shut this off. We start again as of from here. We are not sure whether it was the air conditioner. We're not positive that that was the cause. It may have been something else, okay? And we don't want to have to wait as long. Let's say this process went out of control around here. We don't want to wait as long to get to the alert, to detect it. So what they discovered is that if we start here somehow, okay, if we start here, then if it's still out of control, we'll find out a lot faster, okay? And if it's in control, this thing will tend to go down. Okay, so they found this as the FIR as a nice trick, that when you restart the process, you start it from there, you don't start it from here again. It's for restarts. It's not for you know, not for, if you would have started if you started the process early in the morning, right? You come in every morning. In the morning, the system shuts down at 6 o'clock, and you come in at 8 o'clock in the morning. You start the process going again. You would not, there's no need for FIR, because the thing is going to be in control. Most likely it's going to go down, okay? But the incentive, the motivation for developing FIR, fast instant response, is for when you restart the chart after it went out of control, okay? Now, once you run FIR and it helps you, you will run it all the time. And when you start in the morning, yeah, we'll start here, we'll go down. Okay, but then if it breaks down, it will start from here and reduce the ARL, reduce the time to detect the condition of out of control. Is that clear? And I believe that mathematically, what you do is equivalent to starting from h over 2. Okay, I don't remember the exact the expression, but does that make sense? Yeah, if you go back and look at it, it'll start from h over 2. So that's the FIR. So the FIR exists for all of those, for both the UMA and all the both accumulative charts. QSUM and UMA have a fast initial response mode. I didn't find, experimentally, that it really helped all that much. Right? From what I recall in the video, it wasn't like a wow. The QSUM was a wow. You know, it really made a difference. But the FIR, but it makes sense to do that, and so that's it. So did this, did that. Now I get to problem 2. Unless there's a follow-up question on this at all. So problem 2. So you have, okay, this is my personal comment to the subject matter, and it's illustrated with problem 2, is that there are 2 kinds of questions that you can be asked on an exam, okay? There's the mechanical questions. Here's a bunch of data, do it, press that. And then there are the conceptual questions, okay? So and the conceptual questions, which is almost like this one, it looks, oh, what do I do? How do I get, where do I start? Okay. So the conceptual questions are more difficult, okay? The nice thing about the conceptual questions is that they do require you to think, which is kind of nice because I used to think that quality control is a pretty dry subject, which doesn't really have hard questions. All you know is you have the chart, you have the data, you build a picture, you know, what else is there? But you can ask, there are conceptual questions that can be asked. So what generally our guideline on the exam is to give the bulk of the marks for the more straightforward stuff, and then to have a certain portion of the marks for the more thinking conceptual questions. Okay, so but there will be some there. Don't get intimidated. Just take it easy. Just think about it and say, okay, how would you start this? So let's think about this question here. So I'll read it. Yes. Is the delta equal 1? Delta, well, what is the sigma? Sigma is 1.5. So delta is equal to 1 standard deviation. Oh, so then no, it would still be small, right? It would still be, it still require a QSUM chart to detect. I mean, you're on the borderline. Is that what the question is? I'm not sure what the question is.
It's just the whole question is for the system. If sigma equal 1.5, is the delta equal 1 reasonable?
Delta equals 1. Little delta, big delta, what are we talking about? We're talking about when I say reason, when he or she says reasonable, I presume it means that can you use the Shewhart chart? Is that what's being asked? Okay, is that what maybe? Well, I'm asking. Are you asking if we should use Shewhart or QSUM? I said 1.5 is sort of the borderline. Yeah, so if you have a sigma of 1.5 and you have a shift of 1.5, then delta is equal to 1, yeah, then then you need QSUM, right? Because you're dealing with little k equal to 1 if it's out by 1.5, right? Yes, well, you have the delta this is the delta in the units of, everything that, it's like standardizing, right? This is the delta in the original units. And then we have this is equal to delta times sigma. So this delta is in units of sigma, and this is delta in units of the original units. Okay, so this is like in centimeters, and this is in standard deviations. Okay, so if the question is, let's say that this is equal to 1.5, a shift of 1. Oh no, let's say she's saying that, or he's saying that sigma is 1.5. Well, that's fine, but how much of a shift are we talking about? If the shift is 1, we need to, that's not enough information in the question. When sigma is equal to 1.5, you have to specify either this or that for me to be able to answer that question.
So we just set a small one.
The small delta is?
1.1.
1, just 1. Okay, so this is 1. So this delta, big delta is 1.5. So we're talking about a shift of delta of 1 for a shift which is like this is the shift, right? So it's small. This is small. You need QSUM for that. Right? It's the number of standard deviations. If you're out by more than 2 standard deviations, if this would be instead of 1, it would be 2. Right, and this would be a change of 3, then Shewhart will detect it. But if you're at 1.5 delta, then you're on the borderline. Say that again.
I mean, if it's like 1.5, then those ones will be on like QSUM or.
Yeah, it's these numbers, these threshold numbers, you got to take them all with a grain of salt. They're sort of generally. The borderline, but the borderline is not black and white, right? If it means that if you're on this side of 1.5, you need QSUM. If you're on that side of 1.5, you can use Shewhart. if you're around 1.5, you know, one, by experience, one may be better than the other. And the border is not definitely at 1.5. There's a confidence interval around that too. So, but that's what they've chosen. And this quality control and statistics is full of these borderlines where there's argument about it. Like it's like the number of samples you take initially, 25, you know? Is for what value of n does the normal distribution kick in? In the textbook, it's 40. I grew up thinking it's 18. And later on, when I grew up, between 5 and 10 is good enough too. But you know, if somebody wants to be safe, then it's 40. You know, so these are shades of gray. I hope the question has been answered. Yeah. So we go to, yeah, so what I was saying is in these problems, you sort of have to go through them and think them through. Consider problem 1, part B. Does QSUM show any shift in the mean? Okay. And I guess you've got this data. It is known that the temperature level in the annealing process that makes a steel alloy, okay, affects the mean of the surface roughness. Okay, so the key quality characteristic is the roughness, right? That's what we were talking about? Yeah, roughness of the steel alloy. And now it turns out that temperature affects the roughness. And he has a function. There's a function that relates the roughness as a function of 2.3 times square root of T. Okay, the hotter it is, the more rougher the steel alloy. Okay, the lower, so that's there. The above, okay. Describe precisely how temperature should be adjusted to bring the roughness mean to the nominal value. Okay, so we have a mu naught equal to 20. And we have to estimate mu 1. We can't go anywhere. If I need to, you know, this, at 20, we're going to have a T naught equal to what? What is T naught going to be equal to? What's the initial temperature? If mu naught is equal to 20. You can do the calculation, right? It's 20 over 2.3 squared, right? So what does that come to? I think I calculated it. 75.61 I get. So I don't know whether this is centigrade or Fahrenheit. Yeah? Yeah. So I presume, let's assume that it's Fahrenheit. Okay, so it's 75 degrees initially, nice and comfortable. And that's the initial temperature. Now he's asking me, describe precisely how temperature should be adjusted to bring the roughness mean to the nominal value. Well, I know that at the nominal value, the temperature needs to be 75.61, right? So how am I going to figure out, why should I adjust the temperature? What is he talking about? It's 75.61. This is that. What's going on? Huh? That's it? We're finished? No. 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 What's going on? What do we need to, what's wrong? Okay, so we need to refer to problem 1, part B. So we did a QSUM chart, right? And the QSUM chart shows a shift. Okay? With the QSUM chart that came out was looked something like this. Oh my gosh, all these noises. Okay, so this is H. Where was H? Capital H. 7.9 something? 7.155. 7.155. Okay? And this guy went actually at this point here, and then he went down, and then he went up. Okay? So do you remember in the videos that the QSUM chart has one nice feature? not only can you detect whether there's a shift or not, what else can you do? Right. You can estimate the mean after the shift just from the geometry of this chart. So it went to here, and it went to there, and I measured about 9.9. Okay, I looked it up the chart. Okay, so I went 9.9, and at observation. Now, this all depends on the QSUM chart that you got, but I got 21. At 21, it started to grow, and it grew till there, right? So it looks like a triangle a little bit, right? A lot. So what is at what point? Around 24, around 25. Around 24, it went across the border, and at 25, it stopped growing. Okay, so we have a period here, and this is called the Ni plus, right? And so we have the Ni plus at 25. This has been positive for 4 periods, right? So this is not a magic formula. This formula is U1 is equal to mu naught, so that's 20, plus you take this value here is C25 plus, so it'll be C25 plus over N25 plus, and then you have to remember that you have to add capital K, so that's little k times sigma. I have to make a K like I used to make in school. Okay, times sigma. And we're okay on this board? We're fine, right? Yeah. Yeah, okay. So we do this. We have 20. We have C25 became 9.9. We have 4. We have 0.5. And there was a sigma given in problem 1, which was 1.5. Right? And when you do the math, you then estimate, this is an estimate, the estimate of mu naught is equal to, I get 23.22. Okay. So the roughness got worse. The roughness went from 20 to 23.22. Okay. Yes. No, this is based on, let's deal with common sense. This is a triangle. So we see it went from 0, you keep track Ni plus when Ci plus is positive. And it's positive and positive and positive and positive and positive. And then it even passed the goal line, but it went as far as that, and then it went down again, so something happened, so we stop it there. Now you might have a question that says, why don't you keep on going, right? Could we have kept on going? Well, at this, Ci is still positive, but you stop after because it's assumed that the process will be stopped at this point, at some point. Once.
They fixed the question. It was a typo. So we just again have even Ni plus the amount of period with Ci more than H.
Not Ci more than H. No, when Ci positive. Yeah, it was Ci positive. Okay, so that's been positive over this because at mu naught is equal to 20, it'll hover around here. It'll be 0. If mu naught is 20, it'll just go up a little bit, come up, and it'll come down. If you notice in the videos, as long as my system is in control, it just sits flat. It's only when I introduce a deviation, then all of a sudden it doesn't go up right away. It still behaves well, but then a few later, all of a sudden it says, "Oops, this hurts," and it takes off. So now, if you want to know what the mu is, well, it grew within this amount of times over that number of periods. So that's our estimate, and then you just have to make this magic adjustment because you took it out of the CI plus, so they tell you to put it on, back in. Okay, I didn't quite prove that, but it's understandable since you added in the CI plus. Do we take it away or do we add it? No, because we took it away. We took it away earlier, so now we add it back in, right? We were trying to get rid of the small deviation, so now we add it back in. So this is 23.22. So this is the mu1. So what happened to the temperature? So we have mu1 is equal to 23.22. Well, what's the temperature going to be now? 23.22 over 2.3 squared, which is 101.92. So the temperature has gone up. If that's true, then it must be warmer in the room. So we notice the roughness. The nice thing about this problem is you don't have control over the roughness. You have control over the air conditioner. Okay? So you now have, the thing that you can adjust is the temperature. You can't adjust. So this is a nice illustration that you can't directly control the key quality characteristic. By the way, that key quality characteristic, it changes name over the course. Sometimes it's called a critical characteristic, critical quality characteristic, or sometimes it's a key. I probably should improve the course by keeping one term throughout, but there is such an animal, right, as the key quality thing, which is the roughness here. So now the answer is I just have to lower the temperature from 101 down to 75. Yes?
So there's another question. We asked for the Q-sum, can you use 20 samples with a mean of 3 and 20 samples with a mean of 41.5?
Well, I don't know where the 21.5 would come from. No, look, I have a process. I'm like these control charts are like diagnostic tools. It's like the doctor's stethoscope. Okay, he walks around with a stethoscope because he wants to detect whether you're sick or not, right? So the quality control stethoscope is the control charts. He assumes the person is healthy. 99 depends how old you are. 99.99999 if you're young. When you go to the doctor, maybe 100%. You've never had, in fact, I'm a little older, but I've never had a doctor put a stethoscope on me and say, oh, there's something wrong with you. Okay? But that is a very good detection tool to detect if there's something sick with you. So control charts are detection. I have reason to believe this is it. I don't know. I have to detect that this patient is sick, right? So I can only run a Q-sum chart and just watch the data. And then when this happens, then I hear something funny in my stethoscope. Okay? The patient is sick. Not only can I now, with the Q-sum, can I say the patient is sick, we need to find the cause, but I can also, in addition, the feature is I can now estimate what it has changed to. So when the question is saying, can't I run it with this and that, I don't know what the other one is. I don't know he's sick until he crosses the border. And once he crosses the border, then I can say, okay, my estimate for his changed mean is so much. He's got a high blood pressure. Okay?
Just added,
yeah, comment?
He just said, check QC. Each compound has a name. They may even set a name for safety relevant, customer relevant, performance relevant, etc.
Okay, yeah. So they have, there's tons of names out there. So the fact that I'm using 2 is okay. Thank you. Yeah, I think it's an important, in fact, I put it in the learning objectives of the course, even though we don't really talk a lot about it. But the first thing that you need to determine before you can start quality control is to determine the quantity which you need to monitor. It's very easy to give you all kinds of problems where you imagine that it's the diameter, imagine it's the roughness, imagine this, imagine that. But when you go to a company, you can't imagine anymore, right? If you start your own company and you want to start a startup, eventually you'll be concerned about quality, the quality of your software, okay? So you have, is it the number of bugs that matter? Is it the amount of time that it takes to fix a bug? Is it the impact of the bugs? What is important? What does the customer care about? Maybe all he cares about is a friendly voice on the telephone, and it doesn't matter how buggy your product is. I don't know. You know, it was an industrial engineer that thought of the idea that, Joanna, when you wait for the elevator, everybody gets annoyed when waiting for the elevators. So they call these industrial engineers, these buildings, it was taking forever to get the elevator. So the industrial engineers came in and said, put up a bunch of mirrors. If you notice, by a lot of elevators, there's a lot of mirrors around. And people entertain themselves watching other people. And time goes fly, and time flies. And they're no longer complaining. Anyway, but so you need to find out what it is that you need to fix, what it is that's going to make the customer happy. And then once you know that, then all these control charts kick in. Actually, not yet. You then need to determine what do you have that is controllable to control what that is. Okay, never mind, that's that. That's problem 2. Any follow-up questions on problem 2? Yeah, I am not sure I fully understood that. Maybe they may have, you know, I say, you know, I'm not sure I understood the question about the means, the running it with 2 different means. So I'm,
The person who asked that question was Jacqueline.
yeah.
So we can ask.
Yeah, unless she's okay. You know, if she's okay, that's fine. But if I misunderstood, please, because I did that with someone else. I jumped to the gun. Okay, what else is there that, so let's review the learning objectives for today. Let's do that, okay, until something else comes up. So maybe if you can just read the learning objectives for today, we can sort of see if whether they, I think there is very few, I think as the course comes to an end, there's fewer learning objectives each day because, anyway, go ahead.
So number 1 is the rules and ways of process capability. You previously covered control.
Right. So when we went from when we went to control charts to process capability, I think those diagrams in the video that talk about phase 1 and phase 2, I think are important. In other words, phase 1, things are a mess. It's no time to look at capability. It's let's get things under control so we can get some predictability into place. I mean, it's a mess, right? So we got to get it under control. And once you get it under control, then you don't know whether you need to reduce your variability, whether you need to center. Now you want to know, well, we have something that's controllable, it's predictable, it's steady. Okay, we've steadied the thing down. Now let's find out, what does the user want? How far are we away from what he wants? So now you can, and that's what capability analysis is all about. So you first bring it under control. It doesn't mean full under control. You'll still have alarms, but you need to, you know, there's no guidelines for that. But I think that needs to be decided by management that yes, things are a lot better now, and we can start looking at process capability. Okay, and then you look at process capability. You continue the information that comes from the control charts gives you some of this mu and the sigmas that you need in the capability analysis. And you also can continue using your control charts to reduce your variability, to monitor that. But the process capability starts later in phase 2, and that's it. So that was what that was about. The next.
So the next one is extended process capability concept of using user specification to instances than only attribute data. So effective and defects in accessible. I think I think it is. So it's extended process capability concept of using user specification to instances when only attribute data is accessible.
Yes, thank you. Is that clear? Yeah? Because a lot of the things that we do in standard process capability like CPK and CPM and all that stuff, you don't have the data to calculate those. You don't to calculate the CPs and so on. But there are other indices that are there, and I introduced those, and they're, you know, you can look at the video. I don't remember them all right now. There's one that has a cute name with the number of opportunities. You just, you know, it's like per million. You know, so those things are used. So that's the second one. Any question? Okay. Third one?
So there's 2 questions.
Oh yeah, please.
So they asked when we started
Okay, so the way it works is like this. We cannot bootstrap the, okay, let me revert. When you're dealing with a normal process, right, the normal distribution, you're talking the X-bar charts, then you can decide on the frequency and the sample size before you start, because you don't need to know sigma. So you can decide to reduce your ATS as much as possible, and then you get an N, you decide on the frequency, and now you need to estimate sigma in order to build the control charts. What is at the root of this is really the central limit theorem. So the central limit theorem is like 40, right? That's a lot. But the central limit theorem also kicks in earlier. So I think 25 is like sort of the compromise, so that I know that after 25 samples, I have enough samples that the central limit theorem kicks in, and they're normally distributed. The means are normally distributed. If I only collect 5 samples, then they're t-distributed. I don't want to deal with t-distribution. So I want my number of initial samples to be large enough so that I can count on the central limit theorem to tell me that my means are normally distributed. And we're plotting means, X bars, right? So that's why I need a number of samples that's big enough that the central limit theorem kicks in. Whether it's 25 or 30, depends on the cost, you know, but let's say 25. Now you've collected, you've built your chart. Now you start to use the chart to find assignable causes. Every time it goes through the ring, a bell rings, let's find the cause. Fix the cause. Start again. A different cause. Start again, depending on how many things are wrong, right? So imagine the first week you have 22 alarms going on, of which you detected 10 you could trace down, and the other ones you never found why. And the next week you have 15, and again you try to fix it. You're using the same chart. Now, let me correct. After you've fixed your first assignable cause, you have changed something. So your process has changed. So you need to collect another 25. So this lasts until you hit the alarm, until you get past the alarm. You look for an assignable cause and you change something. You fire someone and rehire someone. You fix the air conditioner. You replace the machine. You now have a different process with different statistical properties. It's a new ballgame. So I need to collect another 25 samples of the new process. And that goes on until I do the first assignable cause. After each time, when I change the system, I change something in the room, I change something in the process, I need to collect another 25. And start again. And start again. Until it becomes under control, then it lasts a longer time, but eventually it'll go out of control. I'll need to collect another 25. Okay, that's the pattern. Like I have a stethoscope, and I need to fix the stethoscope whenever the stethoscope is dependent on the patient. So I first have to learn something about the patient, then I can get a stethoscope for that person. And when that person changes, because I give him pills, then he changes. So I have to get another stethoscope for that person. Okay, I need to keep on changing the tool to match the process. And that's how life goes on and on and on. Okay, so that's, now the sample size is based on ATS. So I decide once, and that's it. Now things may change. The ATS is related to beta. Beta will depend on, won't depend on sigma in that case. So maybe it will not change. It's just M and K. It's just okay. So does that answer the question? Long answer. Is it clear? What, there was another question? No. Yeah, so that's now if you're dealing with binomial and defects and defectives, then you need to have a p-bar to begin with. So again, you need to collect a large sample to get your initial p-bar. But the concept is the same. You use the control chart until things go wrong, you fix them, you collect another large sample, build your control chart, wait until it breaks down, fix your control chart, break, so on, and keep on doing this. Okay, okay. And this is important because we get so hung up in exactly how you build the control charts, taking out the out of control points, the mechanics of it, that we lose the bigger picture of where this where this stuff fits in. So, yeah.
Just a comment for you, because
Yeah.
I know the topic is N for control chart, but an example. In capability analysis, my former company required N more than 125.
Now, was this for defects or for variables? Okay, so yeah, I think for N, when we're talking about sample size, if you're talking about defects or defectives, the sample size are much larger than for variables. For variables like 5 to 10, sample size is more. So I would like to know the answer from Zuko, if you please. Was it for defects and defectives and defects, or was it for a variable? It was for variables. So they wanted a large. Now, is this a sample size or the number of samples?
Because for variables, not sample size, and call it N.
And like the number of samples. Yeah. So they weren't happy with 25. They wanted 125. Okay. Now, that depends also on the cost, right? It depends on the industry. It depends on how much it costs to get these things, right? So if you have to break these things, like the candies, you have to eat them. I don't know, whatever it is, if you end up destroying the product, then it might be. But of course, management would always want to be sure and asking for 125 if they can afford to. If quality is important to them, they will want to spend the money and they will want to get it right. So it's nice to hear that.
You want to go for per outcome?
Say that again?
Per outcome?
Yes, yeah, go ahead.
So you compare the ARL of the cover control chart with that one.
Long sentence, yeah.
That's the more modern QSUM chart. When there are small changes in process means, process mean and variable.
Yeah, read it again.
Compare the ARL of the cover control chart with that more model QSUM chart. When there is small change in process mean and variance.
Right. So what we're talking about is there's a small change in mean and variance, okay? So we're dealing with less than 1.5 standard deviations. We want to compare that with the Shewhart. I didn't want just, what I wanted you to be able to do is be able to demonstrate. So if somebody comes in and says, why should we use QSUM charts? We've been using these X-bar charts, okay? I wanted you to be equipped to sell a company on doing better with newer charts. So if they've used the X-bar chart for years and years, and they're stuck with that and it's embedded, okay? I want you're learning quality control in 2017, okay? There are new charts around. It takes a long time for these new charts to become accepted and to become entrenched because there's so much infrastructure on the old charts. So I want you to be equipped to be able to demonstrate, okay, that, hey, there's something to be gained. Let me show you this. Let me show you this comparison, okay? Now, there's one thing that comes to mind. I don't want to do it before the final exam because I don't want you to get nervous about being able to do these things because I'm not going to ask you on the final exam to recreate these Excel sheets. Okay, although I want you to be able to do that, I wanted to demonstrate it and so on, but I can post these Excel sheets, I haven't done so, on the website. So if you want to use them, I mean at your own risk, so is that, if you want to, I'm willing to post them there. I was thinking of posting them earlier, but I thought it would cause you to spend a lot of time on dealing with them, and I didn't want to take that away from your basic understanding of the material. Okay, so let's leave that. That's sort of an afterthought. So that's the last one, and that's it. So do you think, having watched the videos, that you think you're able to appreciate the difference between the charts? Yeah, okay. It's for any other question? Thank you very much, by the way, for being we have one more chance tomorrow. Yeah, so the office hour for Monday is from 1 to 2. I won't be there, but Abu and Nushin will be there, and I think they will want to also make sure that well, one thing I should tell you right now, Nushin will remind you again, but there is a video where you run the simulation gives you zeros and ones. And then you can't put them into Minitab right away. Or you can put them in Minitab, but you can't ask for the control chart right away. You have to use basic statistics to calculate the number of defects in a sample. You remember that? You have to be able to do that. Okay, so if you haven't done so, practice it. Okay, this is calculating within Minitab the number of defects per sample, or the percentage defects per, well, once you have the number, then the percentage is easy. But because I didn't know how to do that in Minitab, I had to write to Minitab and ask them, do we need to go to Excel to do this, or can it be done? And they gave me the instructions for doing it the way I did it in the video. So don't forget to look at that and practice it. That's my last word. Nushin and Abu will have some other things for Monday. Please be prepared with questions. We're okay having spent the time there, the resources, but you know, we're coming in Monday. It'd be kind of a shame to sit there for an hour waiting. So I mean, don't do it, because if you don't have questions, that's fine, okay? But if you do have, don't hesitate to ask. Okay, thank you very much. We'll see you tomorrow.